How does quantum communication compare to classical communication? Have you ever wondered how quantum communication stacks up against the traditional methods we use every day? Let's break it down in a way that makes sense. First off, classical communication is all about bits. These are the basic units of information that can either be a 0 or a 1. Think of it like flipping a coin. It can only land on heads or tails. This method uses principles from classical physics, like electrical signals or light pulses, to send messages. Now, quantum communication takes a different approach. Instead of bits, it uses quantum bits, which we call qubits. What makes qubits special is their ability to exist in a state called superposition. This means a qubit can representing both 0 and 1 at the same time. Imagine being able to flip a coin and have it land on both heads and tails simultaneously. This unique feature allows quantum communication to convey much more complex information than classical methods. Another fascinating aspect of quantum communication is something called quantum entanglement. This is where pairs of particles become linked. If you change the state of one particle, the other one changes instantly, no matter how far apart they are. This connection allows for communication methods like quantum teleportation and superdense coding, which classical communications simply cannot achieve. When it comes to security, classical communication has its weaknesses. Information can be intercepted and copied without anyone knowing. In contrast, quantum communication uses a principle known as the no-cloning theorem. This means that unknown quantum states cannot be perfectly copied. If someone tries to eavesdrop, the act of measuring the quantum state changes it, making the intrusion detectable. In practical terms, classical communication is what powers our current internet and telecommunication systems. It is fast and reliable but lacks the security that quantum communication promises. Quantum communication is still in its early stages but offers exciting possibilities, such as ultra-secure communication channels and advanced encryption methods. Recent advancements have even made it possible to send quantum signals alongside classical signals in optical fibers. Researchers have identified specific wavelengths where quantum signals ranges unaffected, paving the way for future quantum networks. In summary, quantum communication represents a significant shift from classical communication. It uses the principles of quantum mechanics to transmit information in ways that classical methods cannot replicate. While classical communication relies on definite bits, quantum communication operates with complex quantum states, opening doors to new technologies and applications.